Hello everybody, welcome to week 11 of Industrial Controls, where we're going to talk about industrial design. Yeah, I've got a PowerPoint for you, and we're going to go through industrial design, and we're going to kind of talk about, how you think about how you should design things. How do you choose a particular component? Like, what are the attributes? We're going to jump into that. So with no further ado, let's jump into there. I'm going to share my screen, and we'll jump into the PowerPoint. So here we go. So last week, what happened? Whoa, how come to the PowerPoint is not the thing? Where's it go? Hold on a second, guys. Oh, it's over here. All right, excellent. So welcome to week 11, where we're going to talk about this. I just kind of want to do a little bit of a cleanup, and we'll go back to week 10. In week 10, we talked about industrial design, and we went through this, and also you started to work on your industrial design project, which is a printing press. We're going to talk about stage 2 for the printing press later in another video. For now, what I want to do is I want to continue the concept of industrial design, and here we go. So let's jump into this week's lesson on industrial design, and we're going to look at the PowerPoint. Now, here's stage 2 down here. Oh, it's stuck in here. So again, I will do a video about stage 2 later for you guys, and I'll let you know. So welcome to industrial design, and this is what we're going to do. We're going to talk about how to actually select the airlines, and we're going to talk about safety systems and fail-safe design and control type pneumatics and electro-pneumatics. Okay, so it's important that we kind of talk about fail-safe. Now, fail-safe design we talked about for Lab 5. So it's just kind of a concept that I think you guys get, and I'm sure you've watched the video on that already. If you haven't, please get on that, because you need to understand what fail-safe designing is so that you can finish off Lab 5. So let's jump into airline selection and talk about why we may have to have airline selection, different types of airlines. What's going on over here is that if we take a look at this, you can see there's a flexible line in here. See if I can zoom in here a little bit more. Yeah, I think I can zoom in here a little bit more. Let's kind of go on a tour here of this car wash area here. What's going on is that this motor here is spinning a brush. Now this brush is moving around, right? So the motor is in some kind of housing, and you can see there's a cable there and a cable there, although those are hoses. Those are flexible pressure hoses. And it's important that they're strong as well, because if something hits this here, I mean, there are moving parts. There are a lot of moving parts around in here. So these hoses have to be very formidable. So they have actually a metal sheath around them that holds them stable. You could go up to this thing and like with a kitchen knife and whack at it really hard, and nothing would happen. It wouldn't break. It's quite remarkable. So you can see there's another flexible hose here, another flexible hose here, and there's this machine over here with a brush on it. For sure, it's got flexible hoses. You can actually see 2 lines coming off of it, and another 2 lines coming off of it here. So we've got some different reasons for flexible lines. One of them is obviously because whatever the actuator that it's going to has to move around. It's got to move around. It's got to go left, right, up and down, and whatever. It could be like, in the bottling assignment, we had a swing arm, and that swing arm had a pneumatic actuator on it. So when it was swinging back and forth, it needs to be able to have a flexible line. So flexible lines are very important. Now, the other thing is that, when we're actually installing devices, I don't know what this is. This is like a big box up here. It looks like it's got a bunch of controls in it, pneumatic controls in it. Out of those pneumatic controls are going to be lines. Now, it looks like in here also, I've got some other lines that are in here. Maybe these are airlines as well. They look a little bit thin. I'm thinking the big black ones are airlines. I'm not sure what these are. They may be pilot lines or control lines. So the actual air that goes to here is big, is like it's a high pressure and it's maybe a high flow. But all of these other smaller lines may be pilot lines, which require very small pressure and very low flow rates. So we have these actuators, and then we use flexible lines. A lot of the times, all of the actuators actually have flexible lines going to them. And the reason is because when we install these things, when you actually install an actuator, either a rotary motor or an actuator, there are some actuators down here. Now, these actuators, as you can see, these are solid lines that are going down to the actuators. Those actuators there probably have a flexible line coming off of this solid line going to the actuator. Because if the actuator fails and they want to install a new one, it's a lot easier if they can just unscrew the flexible line. So almost all of your actuators, rotary motors and actuators, are actually going to have flexible lines going to them. It's a little bit rare to have an actual actuator with a solid line going to it. Now, why do we have solid lines? We have solid lines for air distribution, right? So this is a solid line here, and these are also solid lines here as well. Now, these lines are solid because they have to be protected as well. So if you're gonna have things moving and spinning and all this, wherever you can use a solid line, you want to use a solid line. The flexible lines come out of where the solid lines are, or out of some kind of junction, and go straight to an actuator. These are running lines. These kind of run air down to an actuator. Okay, good. So that's what's going on there. And we can see here that a flexible line is used for, say, a robot or something, a swing arm that moves, or some kind of tool that's on the end of something. Robots use flexible lines. This is really cool. This is a cool actuator. I really like this one. Cool. Take a look at it, dude. This actuator on the end of the robot, it's picking up like a bag. And it's cool. So when the air goes in, this thing kind of grabs on almost like fingers. It actually, expand this. All of these baffles in here have pressurized air in them. And what happens is it actually makes this kind of curve in. It's really cool. Air is actually remarkable. You can make really cool actuators with air. You know what? I'm going to show you a cool actuator, a cool air actuator that I built. So pneumatic actuators. This is a cool actuator. So actuators aren't just like, back and forth and back and forth, and also where we have like a motor spinning. We saw that one actuator that's like a grip that grips onto something on the end of a pneumatic arm. This one's a really cool actuator. I mean, I don't have, I don't have enough pressure in my mouth to open this up. This thing is a hand expander. Actually, this is a medical device, and what this is for is people with clenched fingers and clenched hands, and you see that with people that have lost function in their hands. You see hands like this sometimes. The fingers curl in. It's actually a real medical problem. It's a big problem. It's hard to clean in there. It's hard to trim nails. So this is a device that actually I sell through my distributor, Kintec Orthopedics, and it's a pneumatic actuator, and there's a control box that goes on here as well. And what this does is it opens up the hand, and this expands and opens up the hand, and retracts and expands and retracts. And what it does is it does therapy for someone's hand that's clenched in. There are a lot of other kinds of cool pneumatic actuators that have certain shapes and stuff to them. There are airbags that are used in emergency situations to lift vehicles up and to like break doors, and there are big like clamping devices that like cut through like the door frames and stuff. Those are all running on air as well. Some of them are electric as well, but pneumatic actuators, they're just tubes. They go on and on and on. But I thought I'd kind of mention that so you can get a broader understanding of kind of, the industrial application of any kind of pneumatic actuator. There are lots of different kinds. So with that said and done, let me share my screen and go back to the PowerPoint again. So we've got all different kinds, and these are flexible lines. Now, solid lines are used to actually run air around, say, some kind of manufacturing facility or any kind of facility that needs to have air going to A, B, and C, wherever it is. So we've got some kind of, motor over here. Maybe that's just a wheel with a line on it, but you can see there's a flexible line on it. Now, when we draw flexible lines onto diagrams, onto like kind of, wiring diagrams and hosing diagrams and actual like where we put pictures of real components and stuff. These are not schematics so much, but they are actually diagrams themselves. Now, sometimes you will see a schematic, like in Automation Studio or whatever, you're drawing your pneumatic schematics with all the proper symbols and all that. Sometimes you will see flexible lines on those, but mostly, even though you're running lines directly to cylinders, which often have flexible lines going to them, you can use solid lines in your drawing. If you need to, you can put a flexible line in the drawing, or you can just label it. This needs to be a flexible line. And you will see that in the drawing of the schematic system. So yeah, a drawing of a schematic system is this. This is the drawing, and then you can label things here and whatever you need to do. But the actual schematic is what the actual components look like and how we look at the components, what kind of valve it is, everything else. So the schematic symbols are different than the drawing itself, or the cell drawing. And that's where we use the flexible lines. As you can see, that's flexible. This is a flexible line. That's a flexible line. And there you go. So that's what's going on for flexible lines. Over here, same situation. This is a diagram. This is a pneumatic diagram. It's not a pneumatic schematic. And it tells you that this is a flexible line, a flexible line. So when you're doing this, that's the difference between a hard line and a flexible line. And you know that if it's drawn straight, it's a hard hose. So you have to think about that when you're designing stuff, when you're going into pneumatics. So I'm imagining you guys, you know, in a situation where you are given some kind of machine that you have to build. I'm going to tell you a story. One of our graduates, his name is Evan. He graduated last year. He's got a job with a company called Nahani Steel. Now, Nahani Steel is starting to put more automation into their factory. They have a huge steel manufacturer. They have a huge steel forming plant. I've been there. They have these huge stamps, shake the floor. It's awesome. And then a bunch of other little smaller stamps and things, and they form metal. That's what they do. Now, their system is slowly starting to get automated. Now, Evan was building a cell, and what it was an inspection cell with some pneumatic actuators going to it. And it was looking at parts. It was analyzing parts. And it had some doors that were opening and closing and flaps that come up and down, and that was all controlled with pneumatics. So what he did was he ran a flexible line over to the cell. So from wherever the air supply was, it was a good solid hard red line, and it's designed, you know, to be damaged. It's a lot more formidable than this thing. This is just like a thin hose that, you know, I'm going to use to expand, to run over and to fill up the air in my tires or whatever, right? No, it's a really hard, solid line. He ran that over to the cell, and then on the cell, because there are doors and things that open, and it's a big, heavy industrial thing, he ran solid lines over to where the actuators were. And then he ran flexible, and then he ran that directly into a manifold. And then from there, he ran flexible lines into the DCVs and then flexible lines into the pneumatic actuators. But they were all kind of in the cell already. They weren't near the doors and the flaps and the things that are moving around. So you've got to think about the fact that these flexible lines, you know, they're more susceptible to damage than a solid line. So you're going to think about kind of which. So this is an example of just, I'm trying to imagine you guys in the field trying to solve problems. So, and you're going, listen, pneumatics is everywhere. It's way beyond it just in manufacturing. It's all over the place. It's important that you guys have a good fundamental understanding of it, but that you feel comfortable going in there and saying, you know what, you need to put a flexible line in here. You need to put a solid line in here. You need to change this DCV. You need to add fail-safe design to this system because I can see that it's not here. You may have a runaway load. Let's add that in. So it's important that you guys have to understand this. So what I want to do is I want to jump into safety design. Now, fail-safe design, okay, it manages things that break down. Breakdowns happen with equipment. Now, there are kind of two kinds of safety things that we can look at. One is like human safety systems. You know, they manage when people break down. So, you know, people, they break down. They you know, the humans make mistakes. Sometimes systems break. Humans make mistakes and systems break. And what happens is we are going to think about the human mistake much later in other courses. This is a list of systems that are designed for human failure. We put safety systems up like physical distancing, and we put electronic lockout systems and warning alarms, and you know, we have these special controllers just to design for safety so that it shuts things down if someone doesn't do something properly. We have emergency stop. The list goes on and on and on and on. But for now, we're going to focus on fail-safe design. So we're going to be focusing on fail-safe design, and I want to talk about what fail-safe is. And I know that you guys already watched the short video that I did along with the PowerPoint discussing what fail-safe is. We know that all systems are going to fail at some time. Everything is going to break and shut down and fail at some time. And you have to think about what that situation is and how it's going to be affecting other people. And you have to think about designing so that it fails safe. Here's an example of a fail-safe design. We know that at some point, something in this system is going to fail. Now, we will talk about what's going to happen if an actuator fails, or if a DCV fails, or some other kind of system that's controlling the actuator fails. But for now, I want to talk about what happens if the power goes out. I mean, it's not a very common event, especially in Ontario or Canada, even North America, where we don't have the power go out very much. But every once in a while, the power does go out. And if the power goes out, my compressor is going to stop working. My compressor's not working. I'm not getting pressurized air. But the thing is, I have this air tank here, and that air tank actually has a certain amount of air in it, and it can still run the system for a little while. But after the air tank loses its air, or if a line breaks here, or if a line breaks here, or if this regulator fails, we may have a situation where this actuator, for whatever reason, is maybe in a manufacturing process, and it's the third actuator in a process. Maybe there is a process that has 3 actuators. And to finish a part, maybe it's time sensitive. Maybe the part has 3 actuators, and unless those 3 actuators do their thing, maybe it's heated up, and it has to be done within 4 or 5 seconds. And we have to make sure that that whole thing still runs, even if the power goes down in the middle of it. What happens here is we have a backup tank in here, which is really, really cool. And we have what's called a shuttle valve. Now, I talked about shuttle valves in the 4th lecture when we talked about components. But a shuttle valve is pretty cool. It's essentially kind of like 2 kind of check valves put together. And what's going on is that shuttle valve works like this. If the air on this side is at a higher pressure than the air on this side, then this ball will move over here and air will come out here and it will go down and it will power the system. Because the air on this side is greater than 80 psi, it pushes the ball this way and the air doesn't come out of this reserve tank or auxiliary tank. So what we have is we have an auxiliary or a reserve backup. And this is a smaller tank. Sometimes it's just, a 1/10 the size, or what we call an accumulator, just a very small tank. But it will allow this cylinder to run maybe 1 or 2 times for you to finish a process. Or it could be that this cylinder is opening or closing a door or some kind of hatch or something where a human is involved. And we have to be able to have this thing either open or close for a safe operation. So it's important that we kind of think about safe design where if it's going to fail. In this case, this is a fail-safe design where we're putting a reserve tank in and we're using this valve here, which is a shuttle valve, which decides air one way or the other depending on which one's higher or lower. Pretty cool valve. It's also an OR valve. Yeah, pretty cool. So again, we're talking about industrial application. You already are thinking ands or ors. You're thinking control systems. And we know from the first 2 or 3 labs that you can design a purely pneumatic control system just with air. No relays, nothing. And you can put some degree of logic in there, kind of like if cylinder A extends, then cylinder B should extend. But in this case, you can use this as an OR. The other thing that's really cool is we also have and gates, isn't that maybe not the right word, but and valve. The reason I said gates is because some of you may know the term gate, an OR gate or an AND gate from electronics. In pneumatics, we have OR and valves. So we can add logic with this, although in this situation, this shuttle valve is used for a safety application for fail-safe design. We have another situation over here. So what's going on is that this is pretty amazing. Maybe you didn't know this, but fail-safe design is put into brakes. And what's happening is that I'm going to go on and show you about brakes. It's pretty cool. So this system may be used to run air brakes because air brakes are used in heavy vehicles like trains and trucks and buses. And you've heard trains and trucks and buses make those sounds, and that's going on. So, and this could be used to complete a manufacturing part. It's to power a security gate, which is important for people. You know, no matter if all the power's out, oh, we have this reserve tank, and it still has a couple times where we can run this cylinder back and forth. And a supplementary overuse supply. So essentially, sometimes it could be that this compressor is being used so much by so many other actuators. There's a bunch of other stuff down the line, say over here, and it's running off of this regulator. It could be that for whatever reason, the system may be designed to handle all of that, but it may be that just in an odd situation, some of those other actuators that are coming off of this point down here are stealing so much of the air from this compressor that this system, which has priority over everything else, may not be able to run at the proper pressure. So if this pressure goes low, this takes over and feeds this. Pretty cool situation. So power safety systems. So as any kind of safety system is going to be running all alone, and you guys know safety systems because you've probably seen in an electronic situation where you've seen those lights that come on if the power goes out, and those are safety systems. We can also have a safety pneumatic system that will have kind of a reserve tank. So this type of situation is pretty cool. Air brakes, which are pretty cool, they're all fail-safe for sure. They're fail-safe in a way that what happens is if the pressurized air disappears, a spring takes over and activates the brake. Actually, the only way to release the brakes is to pressurize the system. If you pressurize the system, then the brakes release. When you put your foot on the brake, it actually bleeds air out of the brake system and allows the springs to take over. Again, fail-safe design. It's important that you guys understand how to do this in your application when you're out there in the field designing this stuff. Now, this is a pretty cool situation. Now, this situation leads to the understanding of what you have to do for your design for a printing press. What's going on here is that the printing press has got this big heavy stamp. It's like 200 pounds, and it goes up and down and up and down. And it's raised and lifted by a pneumatic cylinder. Okay, that's cool. But the thing is, what happens? What happens if this thing fails or this thing fails? By the way, why would I have this metering valve in here? Now, you guys know metering valves work in a way that in pneumatics, we only meter out. If you want to control the speed of an actuator, say you wanted to slow it down on its extension, if you wanted to do that, you are going to put a throttle valve on the extension line. So the air coming out of here is going to go through here. It's going to get to here. It's going to see this check valve, and it's not going to be able to go through the check valve. So it's forced to go through the throttle valve, which means that this cylinder will extend slowly. And we want that to happen because I want my stamp to come down slowly, especially if it's in a printing press. Cool. So during extension, during retraction, when I want this thing to lift up, I switch this valve, air comes out this way, it goes this way, it gets to here, it sees this throttle valve, it says, I don't want to go through there. It goes down here, it sees this check valve, and it says, oh, it's a free path, I'm going to go this way. The air goes this way, and it goes this way, and it can make this cylinder retract and lift this stamp as quickly as it can. Now, because this is really heavy, it's probably going to lift up kind of a little slowly. It's going to be struggling. It's going to be working hard to lift this up. So you've got to think about how much pressure you want to put in here to be able to lift this stamp. Okay, so now you also know that if this thing failed, if this broke for some reason, or maybe if this thing broke, like if this valve in here, this area here, it somehow died in here, this thing's going to come crashing down. This is a heavy stamp. We can add something for fail-safe design. Pretty cool situation. Take a look at this. We can add this. Yeah, it's called a pilot-operated check valve. Pilot-operated check valves work in a way where it's a normal check valve, so air will go through it this way. So when I want this thing to retract and lift the stamp up, I send air through here. It goes this way, it goes this way, it goes this. It sees this check valve, it goes straight through it. and it makes this go up. Now, a pilot-operated check valve opens the check valve in the opposition, regularly how air would regularly go through it. So if I were to put pilot air in here, and remember, pilot lines are dashed lines. If I were to put pilot air into here, that would mean that this was open for air to go this way. It's open for air to go from here out. So as I'm making this extend, I am putting air here. Pressurized air exists right here. It's going into the cylinder. It's also coming down here. It's opening this pilot valve, and now air can go out this way. Pretty cool. So if anything fails here, this thing is not going to move. The only way you can make this cylinder extend and the stamp come down is if there's pressurized air right here. It's pretty cool. So fail-safe design is used in runaway loads. I mean, fail-safe design is all over the place. One of them is runaway loads. It's another example of a runaway load. This is the same kind of thing. If this, whatever that heavy thing is, if it's being lifted up and for some reason this DCV failed and or the line failed, what would happen is this check valve is not only just out here, it's actually attached right into the cylinder. It's actually screwed into the cylinder. It's the first thing out of the cylinder. You don't put a line out of the cylinder into a safety device. You stick it right, you actually screw it right into the cylinder. Pretty cool. So now, what's the difference between this and this? I want to talk about control systems. This has metering. You can see that. This doesn't have metering. Why does this not have metering? Any thoughts about that? Well, I mean, you know, there may be lots of reasons. I didn't put metering in so that we could talk about it. It could be that you want this to lower quickly. It could be that you want it to lower quickly. In this situation, if it's a stamp, you're going to want it to lower slowly for sure. You know what? I'm going to jump over and I'm going to see somebody had a comment. I want to know what it is. Apply full pressure? Oh, that's really good. You know what? And the answer to that is no. And the reason I'm saying no is because right here, what's going on is that we don't actually lose any pressure through this. It's pretty cool. This is not a pressure control valve. It's just a throttle valve, which is kind of weird because, you know, you think, well, it's very much like a resistor. And we know that there's pressure loss on either side of a resistor, or there's voltage loss. So what's going on here is the voltage, the pressure loss on either side of this, or the pressure drop on either side of this, is significantly small compared to the pressure that's operating this. Plus, the other thing is that this thing down here, so you want full pressure. So what's going on is that I'm understanding that in this situation, the reason I'm not putting throttling in here is because when I apply this, I want full pressure to go up. Well, the thing is, this throttle valve, if I were to put a throttle valve in here, it wouldn't really create a pressure drop because the flow rate is so small as well. So actually, it doesn't really create a pressure drop. And especially actually, when this thing gets all the way up, and it maybe clamps onto whatever it has to clamp onto, maybe it's lifting something, whatever it is, if this was moving, if it had to move really quickly, then we wouldn't put a throttle valve in here for sure. But you know what? The pressure, because it's actually moving slowly, we don't actually have a lot of pressure drop across here. So putting a throttle valve in here is not going to really lower the pressure. But the reason I don't have a throttle valve in here, and I do have a throttle valve here, is this is being lowered and this is being raised. Well, guess what? When I put pressurized air in here to lift this thing up, that pressurized air is working really hard. And if this thing weighs 200 pounds, if it's a big heavy thing, it's 25 kilograms or whatever, it's going to be struggling to work, and it's not going to lift it quickly anyway. In this situation, the reason I want a throttle valve is because if I don't put a throttle valve here and I put pressurized air here, this thing's going to come flying down. Yeah, think about it. If I didn't have this metering valve here, this was not, the air coming out of here was not being throttled, and I put pressurized air in here, this would go, poof, it would just hit the ground. It would just fly out and hit really quickly. I have to put throttling in here. So in your printing press design, you better be putting throttling in there because, or more specifically, a meter valve. This is called a non-return throttle valve. It's a throttle valve with non-return. Okay, good. So yeah, that's what's going on. So it's important to be able to understand in your design about fail-safe and also just simply for control. In this situation, I do not want my stamp flying down. I've got to put this throttling in here. In this situation, it's struggling to push it up anyway. If I put throttling in here, it would just slow the extension even more, and it would have to work a little harder, I guess, to some degree, because there is a pressure loss to a very small degree. But really, this thing's going up so slowly anyway, it doesn't matter. But again, when it's lowering, I'm going to put a pilot-operated check valve in here to make sure that if this system dies, if any of this dies, this thing's not going to fall down. It could hurt somebody. Cool. So a little bit of industrial design. Now, what I'd like to do is I'm gonna end it here. I'm gonna say that's all I'm gonna talk about industrial design. The reason I wanted to talk about a lot of that stuff is so you have an idea of how to add fail-safe into your system, and also how to just kind of choose the right components for the control system for your printing press. So for now, I'm going to let you go, and I'm going to say there's no homework posted. That's it. You just need to work on your printing press assignment. Now, stage 2, I will do a video for stage 2, and it will be out by the end of Thursday. And that's all. Okay, thanks, guys.